The conditions we have favored the world habitable for life are both miraculous and unique to the planet we call home. Beginning in the 18th and 19th centuries, the Industrial Revolution spurred the developmental mind by enhancing the dream of capitalism, during a time where monetary value ruled societal means in the Western worlds. As countries developed, our economy subdued itself to the rise and fall of the boom or bust cycles dominated by our demand. Based on the current state of our economy and the eventual termination of our wealth of resources, our society will be required to develop more efficient ways of validating, acquiring, and consuming our resources. We continue to exploit the valuable necessities which define our hydrological, biological, and geological cycles, such as the minerals, forests, and water we depend on for survival in this eon. It is estimated that by 2045, our population will exceed 9 billion. Can the planet take the stress? With the evolutionary development of the technology in the 21st century, it is believed that the possibility of engineering and designing mineral deposits will be of upcoming debate in the future amongst the scientific, political, and environmental communities alike. With the increasing rise in prices of oil and gold, there either needs to be a global shift in resource consumption or an environmentally engineered solution to our mineral needs of which we have become dependent on. Supergene gold deposits are found globally, with mineral formation hosted by some of the world's largest deposits. The processes which favor formation of supergene enrichment take place over thousands of years, by which groundwater processes are the key ingredients. By assessing young environments capable of producing high-grade gold deposits, appropriate host rocks, and proximity to gold-bearing suites which contain the valuable necessities for potential, we believe the anthropogenic manipulation of heat, redox, pH, and hydrogeological influences may create a possibility which will open doors for the future of the mineral industries.
We have developed a design to engineer gold deposition through the process of supergene enrichment during the formation of gold laterite deposits. We're going to take a minute to explain to you the conditions under which they form. Supergene formation starts at the surface where an ore body is exposed to the elements. Natural weathering of the body occurs and surface waters act to oxidize the minerals present and yield solvents which dissolve other minerals. Gold is inert under most conditions. However, under oxidizing and saline conditions, gold is mobile in solution. This solution leaches the ore body of its metallic content at the pickup zone, which then percolates down through the regolith to where reducing conditions dilute mineralized solutions, depositing lateral gold horizons parallel to the water table. We refer to the area of precipitation where gold deposition occurs as the drop-off zone. With continued hydrogeological processes, over time, the enrichment of gold leads to the supergene deposits we are interested in.
Dr. Lani Howarth. I am a professor of geological engineering at the University of Springfield in British Columbia, Canada, and I'm here to talk about an idea that my colleagues and I are working on. First stages of research, and might seem a little bit out there, but we're doing it. What if we could engineer an environment that could speed up the process of the creation of an economically viable mineral deposit? Taking a process that takes millions of years and fast track it, bring it down to hundreds, maybe even decades of years. Wouldn't that be amazing? What we need to do is find an area, more specifically a whole watershed that has high mineral and geothermal potential combined with naturally optimal conditions for gold laterite deposits. So in this catchment basin, what we would need to do is set up a geothermal system that would provide both heat and energy to run this whole entire system. Now, the heat that we would get from this geothermal energy would create a man-made intrusion. And how we would do this is we would use horizontal drilling techniques to set up a horizontal piping system at a certain depth from the surface. And in a plan view, this horizontal piping system in this area of the catchment basin would be set up like this. This man-made intrusion would increase the temperature of the groundwater and draw it in, creating a convection cell. We're drawing water in from all sides, creating convection cell. Next thing that we would want to do is pump in organisms that would create an oxidizing environment. It would be from anywhere, maybe several point sources, in above this man-made intrusion. So increase in temperature from the intrusion, an oxidizing environment for biological organisms. The other thing that we would need to do is also pump in a high concentration of NaCl, and all of these key points combined help mobilize the gold and create the pickup zone for the laterite deposit. Now the next thing that would have to happen is we would have to create a drop-off zone. And all we would need to do is just almost flip the switch and just create a completely opposite environment. And how we would do that is down here at the discharge point of this watershed is we would want to create a small dam that would hopefully saturate the area at the bottom of this catchment basin. And this would dilute the concentration of NaCl. So we'd have a decrease in NaCl. Next, we would also want to pump in another type of organism that would create a reducing environment. So we would go from an oxidizing environment to a reducing environment. Reducing. And the next thing is part of this really cool new technology called frozen soil barrier. Now it's a method that they're using right now in the containment of contaminated groundwater that helps in the isolation and the control of the migration of this contaminated groundwater. What they do is they vertically insert these thermoprobes into the ground that lowers the temperature, and in their case they freeze it, but in our case we just want to lower the temperature. So these vertical thermoprobes would go in front and in this saturated area that would completely lower the temperature. So we would go from man-made intrusion, high temperature, oxidizing environment, high concentration of NaCl, down to a low temperature, low concentration of NaCl from dilution, and a reducing environment. And this creates our drop-off zone. And when we saturate this area, what happens is it brings the water table, the lower water table brings up closer to the surface, diluting the NaCl, and that's where the gold gets deposited, on or just below the water table. And hopefully what would happen is this would be a continually flowing system, where water coming into the system and water flowing out of the system, picking up and depositing the gold. And any water that would be leaving the system, of course, would be treated and tested, because we want to minimize our environmental impact and make sure that all the water leaving the system is crystal clear. We're actually here on location, in Colombia, and it's so gorgeous here. Looking at a watershed just over the hill, doing some soil sampling, rock sampling, checking out gold potential in the soils, in the rocks, doing some mapping, checking the soil depth. We're also checking to see how this frozen soil barrier method is going to work in these tropical soils. It's a really exciting time. And if we can pull this off, our imagination becomes reality.
So, to go into more depth into some of the points that Dr. McChrystal mentioned, there are several biological organisms and organic compounds that can create oxidizing environments and help to mobilize gold. The most interesting one is Acidotheobacillus ferrooxidin, which is an iron and sulfide oxidizing bacteria that breaks down these gold-hosting complexes, solubilizing gold in the process. An impressive type of organism that can create reducing environments and help precipitate gold from a solution is Plectonema berryanum. In solutions with a high gold concentration, this type of cyanobacteria will reduce gold chloride to octahedral metallic gold particles. Locations on the Earth that are considered particularly viable for implementing this type of engineered mineral deposition process are those that have a tropical climate with a mean temperature above 10 degrees Celsius, greater than 140 centimeters of annual rainfall, and a thick regolith profile of about 25 to 150 meters. A felsic sulfide-rich bedrock below the deposit is desirable because this provides more acidic conditions which aids in the mobilization of gold. Colombia is a favorable location because it has all of these ideal characteristics suitable for the creation of gold laterite deposits. Also, its high geothermal energy potential, which requires faulted, volcanically active regions with shallow magmatic heat sources, is imperative to providing power for the project. This provides a real-world example of a location on the Earth where and how a project such as this could be carried out today.
The Earth's resources are becoming more and more depleted. With time, a critical level will be reached where traditional extraction methods will not be sufficient to keep up with the immense demands of our global economy. Using ingenuity to design and engineer different methods of acquiring the resources necessary to do so will become crucial. The concepts we've introduced take a step toward making that a reality. Given the tools to implement our design, it would create the possibility of producing both economically and environmentally sustainable ore resources that could support the depleting nature of the current state. By producing alternative and innovative solutions, such as environmentally engineered mineral deposits, the future of our race has the potential to move into a sustainable era.
Sweet. And it's finished.